saying that I was very happy to be there to present you our first results from a work that deal with the analysis of the energy transition scenarios from a physical and economic points of view. So this work has been initiated by Gaël Giraud, an economist, and I think that he is not there. Okay. Because Gaël wanted to find a new approach or a new way to discuss the place of energy in the economy. So for that purpose, the idea was to use a scenario, energy scenario, to start elaborating some coupling, innovative coupling, between energy and economy. Maybe that the originality of our approach is to start first by a physical analysis of a scenario. By using a common methodology and common set of technology data to analyze this scenario. And to assess this different scenario, we have developed a model of the energy sector. And this model has been elaborated completely independently of the economical model and the economical hypothesis. But the challenge was to construct a model of the energy sector that is compatible with economic model, because at the end we wanted to couple these two models. So it was very important to define a common framework between it was very important to define a common framework in which we could work, economists and physicists, and to find some quantities, the same quantities, to define the energy sector and the economic production sector. So it was very challenging for us physicists to try to understand the basis of economical model and to understand the economic quantities. As I will show you, one of the main results of our energy model is an estimation of the net final energy that will be available for the economy, for household and for industries. So, and this net energy is an input parameter of the economical model. So for us, it's the embodied energy, meaning the energy that a transition energy consumes to operate its own transition. It's a key point. And it's a sensitive question because we don't know how this embodied energy is integrated in the scenario, how it is treated in the prospective scenarios. So for us, it's a huge challenge to try to evaluate this embodied energy in our energy model to obtain this net final energy available for the economy. So I will start by present you very briefly the economic model that we have used after to build the model of the energy sector. And this is a model proposed by Gaël Giraud. He presented his model 2 years ago here. And it's a dynamic multi-sector economic model coupled to an input-output Leontief formalisms. So in this model, there is one sector which is specifically dedicated to the construction of gross capital. And this capital is used by the different sectors that produce commodities. And each sector produces a gross amount of commodities, and a part of this gross production is used by the sector itself and also by all the others, as well as the sector that are in charge to construct capital. So it means that, and this, the input-output Levontier formalism are in these two terms. So once this energy is deducted from the gross production, we can have the net production that household to satisfy the house sector need. An important quantity is the investment that the sectors give to the sector of capital to construct new installations and to increase the production of commodities. And we can show that this investment is equal to the increase of the facilities to produce commodities, and it also serves to compensate the depreciation and the damages of these facilities. I'm not going to enter in detail in the economic model, but I just wanted to focus on a few main quantities that we use after to modelize the energy sector. The first one is the gross production of each sector, which is related to the capital of the sector and the productivity of this capital. So it means that the inverse of this productivity is the energy that a capital unit can produce when it runs at full capacity. As been mentioned before, the total investment is linked to the increase of the capital to construct new facilities and to compensate the depreciation and the damages. And the net total production, that is called in the model gross domestic production, is the same of the total investment and the net production of commodities that are consumed by the household sector. So in our description for the modeling of the energy sector, we start from the economic model. And we consider first that the energy sector was an economic sector, but it is treated completely separately at the beginning of the modeling, because we want to have a physical approach of this energy sector independently of economic model and hypothesis. So the energy sector is described as a set of technologies that includes energy sources that generate energy carriers and that are consumed by consumers to satisfy their needs. So here we have the energy sources that are converted in energy carriers that are electricity, high temperature heat, low temperature heat, and fuel for transport. And when I will talk about gross final energy, I will talk about these energy carriers coming from these energy sources. And after, these energy carriers are also converted to be to satisfy the energy needs of consumption sectors as residential services, industry, and transport. So what it is important to understand is that we want to calculate the net final energy available for the industry and residential, and we use this net energy as input parameter of the complete model that integrates the economical and the energy sector models. So it is very important to get this value to know the embodied energy, that is the energy that is consumed to transform the energy between sources and energy final use. Ok, j'y vais petit à petit. Alors, so the first step was to translate economic quantities in physics quantities to describe an energy scenario. So the end sectors of commodities production become technologies that are called by the different scenarios as fossil fuels for electricity, and biomass for fuel for transport or low temperature heat. And the capital is the energy facilities that run at full capacity to produce gross final energy in the form of electricity, heat, and fuel for transport, with the productivity corresponding to this energy capital. And the investment is the real energy required to construct new facilities, new energy facilities, in order to increase the production of energy. And finally, the net production is the net energy that are produced by the capital once the embodied energy, meaning the energy consumed by the energy sector itself, is deducted from the gross production, from the gross energy production. So here I show you visually the model of the energy sector, which is closed of the economical model, with an energy capital that are used to different technologies, and these technologies are producing energy carriers, gross energy production, and a part of this gross energy production is consumed by the technologies themselves to produce energy, as well as energy is consumed to construct these energy facilities. So as before, we can deduce the net energy produced in the form of each energy carriers, and this energy is really available for household energy and the non-energetic industries. So now, how to connect this model of energy sector to a scenario, because we want to use this model to analyze the scenario, and more particularly the dynamic of the transition, of the energy transition. It's quite simple. No, it's simple, I promise. It's really simple. So a scenario gives an energy mix. That means that some technologies are led to be deployed, some are simply maintained, and some others decline. So for each type of evolution, the number of energy facilities will change. In some cases, it increases. In some cases, the number of facilities remain constant, and in some other cases, the facilities are closed. So the scenario gives this evolution of the capital corresponding to the different technologies. And if we know the energy that is necessary to build the increase of capital, we are able to quantify in joule the energy investment that is necessary to make the transition. The scenario is also give us the proportion, the quantity of the different energy carriers that each source can produce. So the scenario say, okay, we have such quantity of electricity, heat, and fuel. So this is also an input parameter of our model. And in our model, we calculate the energy, the net energy available, and the scenario give also the proportion of each sector that it allocates in the different consumption sector. So we can check the consistency between the net energy that we obtain by taking into account the embodied energy and the prediction of the scenario about this consumption energy by household sector and industry. So the main steps is, of course, to identify the main technologies that are called by the scenarios, and to use the same set of technologies for all the scenarios that we want to assess. And of course, it is absolutely necessary to estimate the embodied energy for the investment to construct energy facility, and also to the operation of the facility when they produce continuously energy. We have also, we have to keep in mind that the embodied energy is different according to the energy carrier that this source produces. I mean, the investment is more important when we produce electricity from oil or coal than when we produce heat, for example. So it's very important to distinguish the different energy carriers produced, and also to characterize the embodied energies in terms of these energy carriers. So now the second part is how we calculate the embodied energy. Alors, we wanted to it's complicated. Okay, alors, the methodology that we have adopted is really inspired from life cycle analysis to take into account all the operations that are implied in the global conversion chain. And we assume that the energy investment of each technology, source energy carrier, was the energy consumed to synthesize the main materials that are used to construct energy facilities, because as physicists we need to have an estimation of real materials. So these main materials are concrete, steel, copper, aluminium, and of course silicium for photovoltaic panels. And we need to know what is the part of electricity and heat that it is consumed to synthesize these different materials. So here, for example, I show you all the processes for nuclear electricity generation, from the uranium ore to the production of electricity. And so we tried to cut all the energy chain in different main processes, and for each process we identify the equipment, the infrastructure, all the facilities that is necessary to produce this energy, and we define for each operation all this equipment and the energy necessary to construct this equipment. And this is what we have obtained. And we do the same this time for the operation. So to run all these installations. So to obtain these numbers, it was very hard, and we use a lot of multiple information source, and there is a huge lack of information about materials. Only materials. How many tons of concrete, steels? Even that, it's very difficult to find it. And it's more difficult to have this energy in the different form that it is consumed. Bon. And there are also a big discrepancy between all these values when they exist, and more often all the hypotheses are not explained. So it's very difficult to have confidence on the value that we have, because we don't know the how this value have been obtained. Okay, so from the analysis of several different scenarios, we have identified around 30 technologies to produce the energy carriers from different sources. And in the following, the quantities that characterize each technology source energy carrier is the energy necessary to construct one capital unit, the energy consumed to operate this capital, the energy that this capital produce, and the time being in our model it's 1 year, and of course the lifetime of all these facilities. Very simple. Here I show you a figure where there is the energy investment versus the energy for operation. So the investment in percent is simply the ratio between the energy consumed to construct the installation, different technologies, and the energy that this installation produce during all their life. So I think this is the inverse of the EROI, the physical EROI. And the operation in percent is just the ratio between the energy consumed when the facility produce and the energy that the facility consume, the energy consumed to operate the facility, and the energy that the facility produced. And in this table, I have represented our hypothesis on lifetime of the different technology and the load factor for each technology that generate electricity. So, for example, that we see that the main technologies that are used today have a very, very low investment. Very low investment. These values are the values that we have calculated. So, very preliminary estimations. And the technologies that are led to be deployed in the future, but certain scenarios, have energy investment higher. But the energy for operation, very low, as wind turbine or photovoltaic panels. We do the same for the production of high temperature heat, where the investment is lower than for electricity, and we do the same for the low temperature heat production, where the load factors is of course reduced in comparison with the technology that produce electricity and high temperature heat, and we do the same for fuel for transport. So all these values that I'm going to show, that I show you on these figures, are consistent between them because we see that the investment is the most important for electricity generation and is the less important for heat and fuel for transport. But it seems that these values are very underestimated in comparison of what we can find in the literature when we find some few results. And furthermore, there are many things that we don't have taken into account to estimate this embodied energy. Is the question of storage of electricity and heat for intermittent sources. We don't take into account the investment for capture and for carbon capture and sequestration technology. We don't take into account in the embodied energy the energy cost to dismantle the installation. We don't take into account all the installations used by consumers to consume the energy carriers. So there are many things that we don't take into account because we don't have information and we don't know how much it costs in energy. So I think that for more realistic values, this energy investment could be multiplied by 3, maybe 5, or even 10 to have more realistic values. So now I would like to show you some results that we can obtain from our model. And for that, I took a simplified example of scenario where the gross final energy remains constant between today up to 2050. And I suppose that this gross final energy corresponds to 1/3 of electricity, 1/3 of heat, and 1/3 of fuel for transport. And in this simplified example, I suppose that electricity is produced mainly by fossils and a little bit by nuclear, and all the rest are coming from fossils. And in 2050, I suppose that all the fossil and nuclear are replaced by photovoltaic panels and wind turbines in equal proportions. So what is interesting is to calculate how much it costs in energy to deploy photovoltaic panels and wind turbines. Before, yes, yes.
Don't you change in 2050 the primary source for heat and fuel for transport?
No.
Change only
Electricity. It's not a real scenario. Huh? But if you want, I can skip it. It's for pedagogy, you know, to... But it's okay. So, in our model for the moment, we suppose that the production of energy carriers vary linearly. Okay? And here, this is the starting point of the transition, where wind and photovoltaic increase the electricity generation, and fossil and nuclear decrease linearly up to 2050. So here, I'll show you the energy investment to deploy wind turbines and photovoltaic panels. So here is the beginning of the transition, where each year we have to produce a certain numbers of wind turbines and photovoltaic panels to ensure the increase of the production. So the number of wind turbines and photovoltaics increase. And as we know the energy that is needed to construct wind turbine and photovoltaic panel, we can calculate the energy that it is consumed to construct this new installation. Okay? And at the end of the transition, there is no more new installation that are constructed. So this value are equal to 0. Okay? Now, as soon as the installation are built, we know that we have to store energy to prepare the renewal of these facilities, because they have a lifetime, a finite lifetime. Okay, so we know that when we built a wind turbine at this time, you know that 20 years ago after, we have to replace this wind turbine. Okay, so we need to capitalize energy to be ready to renew this installation. So there are many options to capitalize this energy, and in this example, I suppose that I capitalize this energy each year. Okay, so it means that to have this energy each year, I take the total energy consumed for one installation that I divide to the lifetime of the installation, and that it gives me the energy that I have to store each year to be ready to construct a new installation. And this is why this energy increases as the capital of photovoltaic panels increase and as the wind turbines increase. No. Okay. And when the transition is over, there is no more new installations, so the energy investment used is just to renew the existing installations. For nuclear and fossil, this is different because the sources are declining. So when the transition starts, nuclear and fossil plants stop. And for example, in fossil, even if the number of fossil plants stop, to reduce their production, we have to maintain a certain part of these fossil plants. So we need to invest minimum to maintain this fossil production up to 2050. For nuclear, the energy investment stopped very abruptly because the lifetime of facilities, of nuclear plants, it's around 40 years. So it's the same order of the time duration of the transition. So it's not necessary to renew energy nuclear plant. We just stop and we wait for that nuclear plant stop gradually, okay, until all the nuclear plants are arrive at the end of their life. And this, before I show you the energy investment, and here is the energy for the operation to run fossil and nuclear plants. And of course, as the plants close, the energy to operate these facilities decrease. And I remind you that for photovoltaic and wind turbine, we suppose that the energy for their operation is equal to zero. Okay, so what is interesting here? So please stay with me. It's important. In this figure, I show you the gross electricity generation, which is supposed to stay constant. This is my hypothesis. And here in dot lines, I have represented the net electricity generation. It means the energy that will be finally available for household sector and industry sectors. And so we see that there is a difference between the gross and the net electricity generation. And during the transition, this is where the gap is the most important, because we consume a lot energy to deploy new sources. And here it's for electricity, and here it's for heat generation, and we observe the same trend. Okay, and I remind you that electricity and heat is the most energy carrier consumed as embodied energy. This is our hypothesis. We assume that the energy that it is consumed to construct is only electricity and heat, high temperature heat. And we see that for fuel for transport, the trend is completely different. Because we see that as the gross production stay constant, we see that the net production is increasing after the transition. So it means that the new energy mix after the transition consume less fuel than the energy mix before the transition. So we can quantify the efficiency of an energy mix before and after the transition. And we see the importance to distinguish the different energy carriers. Because we see that at the beginning, there is 1/3 of electricity, 1/3 of fuel transport, and 1/3 of heat. But after, when we look the net energy production, the distribution has changed. It's not the same anymore. And here, this is the global curves. So we find the gross total energy, constant. Here, this is the total net energy, okay? And here, I have represented the evolution of the energy investment in orange and the energy consumed for the operation. So it's interesting because we see that the difference between gross and net total energy is the same before and after the transition. But something has changed. And the change is in the investment, which is quite negligible today, but it is very more important where new renew technologies are deployed. And the energy for operation, consumed for the operation, decrease. So after the transition, investment and operation have the same weight in the energy consumed. Okay, 10 minutes, 5 minutes? Now, because I just wanted to show you real results on a scenario, okay? No. Okay. 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 Alors, oh, I'm so sorry. You didn't see the end. Ah, c'est dommage. Non. J'y vais vite. Okay. So, we analyzed two scenarios. The blue map scenario from IEA and EcoFIS that Jacques showed before. And they have the same objective to reduce CO2 emission, even if EcoFIS is also to reduce nuclear and fossil to zero production. But they have two very different mix, and the energy carriers produced are also very different. So, for example, for the electric mix, we see that EcoFIS doesn't use any more fossil and nuclear, and it is only based on renewable energies. And for high temperature heat, we see that the value that in 2050 is much more reduced comparing as today. And again, there is a few fossil use to generate high temperature heat. And here is the same for land temperature heat and for fuel for transport. So the mix, the energy mix are different between these two scenarios, and the gross energy productions are also different, because blue map increases the energy of around 30% comparing as today, while EcoFIS decreases the energy of around 12% from the value from the present values. So here I just suppose that both scenarios produce the same energy to see the effect of the mix only. So I keep the same mix, but I fix this mix has been normalized to the same energy as today for both scenarios. And first, I would like to show you the sensitivity of the net energy according the values that we use for energy investment. And for example, here, for EcoFIS, we have the gross energy that is supposed constant in the first step, and the net energy. Here, with the very minimum values that we have estimated from our material, we see that the net energy is increasing after the transition. But if we multiply this value by a factor 3 or 5, the situation is completely different. So this is what I wanted to illustrate the necessity to have good precision on this energy investment and on these embodied energies, because otherwise we cannot obtain relevant information on the transition and on the comparison between the scenarios. And so here I compare blue map and EcoFIS. This is the net global energy. So we see that there is a difference between the two scenarios. We see that the energy consumed for operate the facilities are the same in the two scenarios, but the investment for EcoFIS is twice higher than for the blue map scenario. Now, this is the real results when we take the scenario, the real scenario, and I will finish like on this. Here I show you the electricity production from EcoFIS. This is the gross production predicted by the scenario, and here is the net electricity generation that we calculate with our model of the energy sector, and we can see that all the two curves behave at the same trend. But for high temperature heat, the behaviors are completely different. And we see that for EcoFIS, the high temperature heat that is consumed for the transition is very, very important. And even after the transition, the high temperature heat production remains very, very low. And I remind you that these values are supposed to satisfy the need of industries, of households, and so on. So we obtain the same for blue map, where the evolution of the gross and net energy are smooth and not so different from today. So we are sensitive to different scenarios. And I will end by this: how to couple this energy sector model to the complete model that integrates the economic model. It's very simple, because energy sector is one of the other sector that produce commodity. So it means that energy is a commodity. And from our energy model, we have the total net energy in the different form of energy carriers: electricity, heat, and fuel for transport. And we know that this net energy provided by the energy sector is consumed by the industry to produce and to construct the capital of the industry. So at the end, we have the energy consumption of the household sector, and we can also compare the energy investment in comparison with the global investment that includes economy. J'arrête.
So I will take 3 questions, and then we will have to be at the restaurant at 1, 2, 3, and after we will see if we have time for the 4th.
Yes, thank you. Yesterday for dinner I was telling you that I was a bit skeptical about your model, but now that I see, I changed my mind. It's an excellent model, and you made a good job in mixing physics and economy, in the sense that I didn't see much economy in your model. It was all physical, physical units all over. But anyway, the question is, you know that there are 3 stages of these things. First is physics, you evaluate your quantities. Then economics, how much it costs. Then is politics. What are you going to tell to the public or to politicians? That you skipped. You didn't tell us anything.
Okay. Alors, in fact, it's okay. So we didn't do this coupling. We see how to make it, but we didn't do this. Here we have to mix commodities and energy. So for me, physicist, the only way to do that is to put euros, dollars, on all these quantities. But I know that behind these quantities there is energy units, joule. Okay? So to do that, after we have to work hard with economists, because we have to apply prices. I'm not very familiar with this term prices, but and I don't know how we put prices on energy. And this is why, for us, it's very difficult to understand the scenarios, because they are built from economic consideration, and we don't know this economic consideration. So I'm very exciting to observe economists to put some prices on it, but this is only what I can say. Sorry.
You mean interior prices?
Yes, of course.
Because the other prices are.
But we have all the information. We have materials, we have energy, the different form of energy, we have all the information.
So I didn't understand well how much accurate is.
Who is
the
talking?
model.
Sorry.
Yes. Farah Hariri from. So Farah Hariri, physicist from CERN. I would like to know how much accurate is actually the model. So how do you validate the model before using it for analysis?
So we are very far from validate, not the model, because the model is a model, but the parameters that we use in the model. And what is really critical is to obtain values on energy, on materials, on energy consumed to construct. And I don't validate the values that I have shown. I don't know if they are correct.
Evaluate the accuracy of the model at the end of the day before saying how much precise is the model before I can trust that I can fix. This is what I don't understand.
Yes, you want to use a real case to prove the model.
What's the sensitivity to parameter change?
Yes, absolutely, and we have to do this. We have to change the values of energy investment that we don't know. We can change the time of the transition, the lifetime. We have many calculations to do to compare the sensitivity of these different parameters, of course. But to make sensitive calculations, we need to know the range of the values, the minimum and the maximum values. And we don't have even the beginning of a correct value to do that. So I make a call here. Please, help us. We are completely disappointed.
So thank you very much again. I have to cut it here.